Right here in Denmark, in the city of Copenhagen, a team of 75 people is building a new type of nuclear energy. They use thorium, a mining waste product, mix it with molten salt, put this liquid fuel into a shipping container, where it flows through an onion-shaped ball of metal, where the thorium is transformed into uranium. And then they split these atoms, which releases huge amounts of energy. My question was, why? Why thorium? How can a waste product power our future? And speaking of waste, what happens with the nuclear waste? And why build a small reactor when you can build a big one?
Small nuclear power plants.
Smaller and quicker to build than a traditional nuclear power station.
Thorium is ready now.
Copenhagen Atomics is building molten salt reactor.
Manufactured entirely in a factory.
With the promise of power that is truly limitless.
We are building thorium molten salt reactors based on our onion core design that fits inside of the area of a 40-foot shipping container. Something that is mass manufacturable, that is affordable, and that can be easily deployed to anywhere in the world. This is like a crazy tech startup because it takes so many years to get from the point of founding the company until we are cash flow positive. This is where the magic happens, so to say. I was already interested in energy before we started the company. I had already invested in other energy sources, for example, wind. And then I stumbled across something on the internet called thorium energy. I've never heard about thorium energy at that point. And I had to admit, in the beginning, I thought it was a hoax. I looked at it, it just looked too good to be true, and nobody was using it. So I started researching more and more to figure out what is it that they're not telling us. And I found out that there's nothing missing. It's just because it's difficult to do it back in the 50s and 60s and 70s. There was a guy called Alvin Weinberg. He actually tried really hard to make it happen, but it didn't happen back then. I think if we didn't have the internet with all the information and the simulation tools, the computer tools to figure out how this thorium energy worked, we wouldn't have started this company. So it was sort of the perfect moment, and that's why it started at that point in time. We humans have been here on the planet for hundreds of thousands of years. Most people in Europe worked on making food and clothes. It was very difficult to scale society because almost all people were just using their own body and their own energy. It was only the kings and queens that had access to all of the food that they would need and a proper house. It was a really tough life for most of that time until about 100 years ago. Instead of using horses and slavery, we started using energy from coal and oil, and especially in the last 50 years, we have really mechanized everything we do. You can go down to your grocery shop, get whatever you need, and we have access to steel, so we can build tractors and other machinery. All of that requires huge amount of energy. Building those materials for the factories and for the tractors and for the roads. We have scaled our energy consumption by 10x, and we expect that we will also grow it by at least 5 or maybe 10x over the next 100 years. 8 billion people in the whole planet, roughly. And everybody, all of the 8 billion people wants more energy to build more AI and build more robots and build more whatever self-driving cars. If you look at all of the energy sources that we have today, none of them are able to scale at the level that we will need over the coming decades. Our goal is to produce an energy source that is cheaper than coal right now. Coal is still the cheapest energy source in most areas of the world. Unfortunately, still a lot of people in the whole world that cook their food and heat their home with some sort of a fuel that they burn in their home. In a country that is developing, it doesn't really matter whether it's green or not, it matters whether it's cheap. The only way that we can offset that is by having an energy source that is scalable, that is affordable, and that is clean. Of course, there's fusion, which I looked at that. I spent a significant amount of time trying to understand when will fusion break through as a technology, and I decided that it's unlikely that I will see fusion in my lifetime. And this was around the time that I actually discovered thorium, and I realized thorium is much easier than fusion and also will be cheaper. And that's of course important because if you have something that scales as well as fusion, but it's cheaper, then it will be even more difficult for fusion to break through. So that's essentially why we started working on thorium energy.
Thorium is an element in the periodic system. It's a metal that you can find basically all around the world. There is about 4 times as much thorium in the world as uranium, but the difference being that uranium, you can only use 0.7% of that, the uranium-235, to actually use in the reactor, whereas the thorium-232 that we dig up from the ground, we can use basically right away. In that way, there is actually thousands of times more thorium that we can use compared to the uranium. The amount of thorium that you would need to produce all of the energy that you need in your entire life, houses, schools, hospitals, the roads you use, all of the cars you're going to use in your entire life, the planes that you go on, so on and so on. All of that energy could fit inside of your hand. So here, this ball, that is what you would need to power your entire life. That ball would cost you around $100. Right now, we dig up quite a lot of it already when we dig for rare earth metals around the world to use in solar panels or in constructing our phones. But right now, it's just a waste product. That also means, of course, that thorium right now is super cheap. We would like to use that. So now we are coming up to the production facility that we have here in Copenhagen Atomics. We have a lot of things going on in terms of our production of both the different components and test systems that we sell, the production of purified salts and so on.
What we have here is salt powder. It looks like this when we buy it from the chemical factories that make it, purify them, and eventually we melt it and it becomes a molten salt. And then when that molten salt freezes again, it looks like this. So this is an ingot of molten salt, roughly 1 kilogram. These pumps are made for pumping molten salt at up to 700 degrees Celsius. When we first wanted to build some of our first test systems, we actually called many pump companies and asked them if they had some pumps that we could buy and modify so we could use them for molten salt. But it was not possible for us to find any company that had molten salt pumps. So in order to just have the internal discussions, I was drawing this pump in a CAD system. And then I decided after I had drawn it that I wanted to print it in plastic, and it worked. It worked actually quite well, like after a week. And then I decided, okay, that was not difficult, so I decided to 3D print it in metal. Unfortunately, that didn't work. But then, we spent some money and we decided, okay, let's mill out of steel parts. The way this pump works is that down here we have an electrical motor, so basically a three-phase electrical motor, just like it was invented more than 100 years ago. And up here at the top we have the impeller and volute, which is what pushes the salt around and basically the pumping function. So this particular coupon has never been exposed to salt. So this is a brand new one. And then this one has been exposed to our molten salt, Copenhagen Atomics molten salts, for 1,000 hours at 600 degrees. And you can see very little change. And then this third one here has been exposed to the same salt as this one, but without the Copenhagen Atomics purification. We do a lot of this testing to figure out how different materials respond, also at different temperatures. So there's a lot of testing has gone into this. One of the problems with this one is that it needs service every now and then. The goal of this one is to have a pump eventually that can run for 10 years in this very harsh environment with molten salts, very high temperatures, up to 700 or 800 degrees, and with a high level of radiation without any service for 10 years. This is like super difficult. This one here has electromagnetic bearings, meaning that all the rotating parts inside are levitating on a magnetic field when it's rotating. And this means that no surfaces are grinding against each other. We haven't finished the R&D for this one. This is still being developed, but hopefully in a couple of years, this one will also be up and running in many copies.
This is our loop hall, or essentially test loop hall, where we are running a lot of tests all the time. This one is our longest running loop. It has been running for more than 2 years now. So that's hugely important for us because we have to prove that our components are reliable. The reason why the hands are sticking out, we get that question quite a lot, is because there is a little bit of an overpressure with argon inside. We need to have an inert atmosphere where there is no oxygen. The salt sort of captures the oxygen. It also sucks a lot of moisture out of the air. So we want to keep that away because that is what is causing the corrosion. This would be the cold side. where you have the operating system. That's essentially what's controlling the entire loop. This is the hot side. You see the insulation around. These down here and up here are the heaters, and that's what heats the entire oven to around 600 to 700 degrees. You have the salt here, which is being heated up, and then it's being pumped around in a circuit. So here we have a loop that was just opened. You can see that it has been used because the metal is darker. There was a bit of a pressure sensor that was bugging, so they think there might be a blockage somewhere. Hopefully, they said it's an easy fix, but let's see. We have this iterative approach where we test something until it breaks, then we look at it, we examine how well it has performed, then we iterate that component, and then we test it again. In that way, we can really optimize very quickly the components before we move on to sort of the prototype reactors, where the testing cycle, so to say, is much longer. I mean, these loops we can power down, so to say, and cool down in a matter of hours. But if it was to be in the full-scale prototype with a molten salt reactor or molten salts, then it could easily take up to a month if we wanted to do a new test. Therefore, it is very, very important that we make sure that the components work before we start testing it in a both more expensive and more time-consuming test. Because we have taken this approach where we have built a lot of stuff and we have tested it so much, we are actually also at a place where we are selling these loops and other components, I should say, to customers around the world, mostly universities and national labs, but also some of our competitors that are in the molten salt field, because we have quite extensive knowledge by now on testing in a real-world scenario.
Here we are standing in front of the only molten salt reactor prototype we have at this location. This end of the reactor is the cold section where it's a sort of room temperature. And then there's the other end of the reactor where there's the black insulation around it, because it's 600 degrees C on the inside and the insulation is there to not heat up the room too much. In front of it here we have 5 tanks. These 5 tanks are full of salt, roughly 10 tons of Fleenac salt. And what we do here is we heat up the salt with electricity and then we pump it around and do a lot of mechanical tests. It's very safe to work with these reactors and we can learn a lot of things. We can even intentionally make mistakes where we spill salt so we can practice of cleaning it up. So when we build the next one, then we fixed all the mistakes and bugs that we see with this one. The reason why these molten salt reactors are very different than traditional uranium-based reactors or light water reactors is that in a traditional reactor, the fuel is in fuel rods made of uranium oxide. That's completely different here. Here, the fuel is molten. It's a molten salt that has the same viscosity as water. So the fuel flows from the bottom towards the top. And while it's here in the middle, this is where the chain reaction happens and this is where the energy is created. And all these other things are there just to make it work and make it efficient. So when the neutrons are created in this channel, they fly out in all directions and they fly really fast, almost the speed of light. And then in these 2 tanks of water, they are slowed down, and then some of them are returned, bounces back into the fuel channel where the next reaction happens. So when the salt comes in down here at the bottom, it's at 600 degrees, and when it leaves at the top, it's 700 degrees. And it takes less than a second to pass through here. So in less than a second, we heat up the salt by 100 degrees. So this is where a lot of energy is created as heat. And then later, outside the building, in another building, we convert that heat into electricity with a steam turbine. When the neutrons get out here, they get captured by the thorium, and then slowly over, say, 30 days, the thorium automatically converts itself into uranium-233, and then we can insert this uranium-233 into the fuel channel, and that's why we don't need to reload fuel like traditional reactors need to. That's part of the reason why we can get the price down. And this is something that none of the other reactors have anywhere in the world. And because of this shape of the blanket, it now becomes possible to generate a positive impact on the price. This is actually one of the early designs of the onion core. We use this one for testing software. So whenever we have a new software release, we can test it on this one because it's really quickly to run a test here. whereas on the one with molten salt, it takes more than a week just to get it up and running. Outside to some other, here's some buffer tanks, and then there are some steam converters, and those steam generators basically convert the heat from the hot salt into steam, which can then drive a steam turbine. The salt that comes out of the reactor is not radioactive. There is some other salt inside the reactor that are radioactive, but we use heat exchangers to bring the heat from the radioactive salt over to a non-radioactive salt that can be sent out of the building.
The nuclear industry is highly regulated because of the hazards associated with nuclear power in general. One of the challenges for Copenhagen Atomics is that we work on molten salt reactor technology, so it's a fluid fuel which is quite different to what most reactors in the world are today. Big challenge is the fact that the regulations as they're written today and the guidance that support all those are focused on light water reactor technology, which makes it quite a challenge to sometimes demonstrate that you comply, and it also comes with challenges with regulators and regulatory bodies, and the people within the regulatory bodies not necessarily having the confidence or the understanding of this technology. We have to find a way to meet those regulations in often novel ways. It's not just written down exactly how to comply. We have to come up with our own approach. We have meetings with regulators, so technical meetings where you discuss issues. Best approach is for us to propose a way forward, so propose a strategy. This is how we want to license it. This is how we will meet the regulations, so the law. Every country's regulatory framework is different, and every regulatory body is also different, so different people, different processes. At times it can be frustrating in terms of getting meetings scheduled, getting the discussions. We chose Switzerland as the location for our test reactor. We have this agreement with the Paul Scher Institute, PSI.
I thought actually I'd give you a bit of an introduction who we are, why we came together, from where we come from, and why we also think that Copenhagen Atomics and PSI are a good match.
We are looking to apply for a construction and operating license for our test reactor, and we're looking to do that in the next year or two. That will allow Copenhagen Atomics and PSI to construct this facility and then hopefully run out molten salt reactor technology.
It takes quite a lot of money to go through approvals and build this stuff. So we need to raise quite a lot of capital. Right now, towards our test in Switzerland, we have to raise 200 million euro. That, of course, is quite a lot of money. And that can be a little bit difficult to raise, especially with still some of the stigma surrounding nuclear, but also, of course, being a European company. The risk-willing capital in Europe, there is a bit less of it in Europe, which is a pity. And because of the very segmented sort of regulation around investment and stuff, that can also be a bit of a hindering towards getting investments from European companies or capital funds. So we might have to look outside of Europe as well to find that capital. And after that, we will obviously have to raise a lot more in order to start building these gigafactories and such. But at that point, the concept and the sort of technical challenges have also been more or less proven with the test in Switzerland. So that should also make the risk quite a lot lower.
Will you stay in Europe or will you leave?
Time will show. It really depends on, first of all, where we would get the investment from, or investments. Perhaps there is like one country that will just focus super much on this and really want us to move there. Then maybe that will be the case. It could also be that there is just one country that both want to invest and also want sort of to have the gigafactory there and wants to deploy a lot of reactors, and then it might also be necessary, but it could also be that that would just be a subsidiary or something. You never know. So, yeah.
This really shocked me. It's sad to see that they might have to leave, even though they're building world-class technology here in Europe. And that is exactly why I'm making these documentaries, to show that we can build and to push back against the general pessimism in Europe. If you feel the same, tell your friends, co-founders and investors that a dedicated, forward-looking team exists here in Europe. Let's make sure that they can stay and keep building the future.
If we look at nuclear reactors today, the ones that are being built in Europe, if you start to analyze how the cost of those are distributed, around 10% of the cost is materials and the labor cost to build it. But unfortunately, there is very, very high requirements that every piece of material, every component has to be documented, and this makes everything super expensive. If we look at some of the classical nuclear reactors, they have some very expensive pumps, can easily cost $20 million. The weight of the pump is maybe 40 tons, but the weight of the paperwork that they need for the pump is more than 40 tons. You know, millions of pages of paper to document that everything was done correctly with that pump. And they of course need many, many more engineers and technicians to write the documents than to actually build the pump. And I think that's a problem. I think that's some of the things we need to fix in the nuclear industry.
A lot of people, especially the older generation, have a very negative perception of nuclear. And it almost doesn't matter what you say, they just don't like it. And there is a perception that nuclear is really unsafe. That is simply not true. If you look at all of the reactors that we have built and the amount of energy that has produced, comparing that to any other energy source, nuclear is one of the safest forms of energy that we have today. It's sort of like when a plane crashes, right? It's something that you hear about and people get very scared about it. And I think a lot of people are more afraid of flying than driving a car, even though you are much more likely to die in a car crash than in a plane crash. And that's sort of the same with nuclear. A lot of people are also worried about the nuclear waste, but nuclear waste we are exceptionally good at handling in the world. We have handled that for, 80 years now. There is nothing dangerous about it and it has never killed anybody. But a lot of people are worried about it. And I think, a lot of people might be thinking about this green gooey stuff that is in The Simpsons. That is not what nuclear waste is. In a Copenhagen Atomics reactor, we can use almost all of the fuel that we put into it. And that's because we are burning both all of the thorium that gets upgraded, so to say, to uranium-233, that can then undergo fission, and then we can remove the fission products from the fuel salt, and thereby keep the salt sort of clean. We then have much less what's called waste. The waste profile from a Copenhagen Atomics reactor would only be the fission products, but not the long-lived radioactive elements such as plutonium. Instead of 100,000 years, you can store it for 300 years. So in this way, it is very, very different to a classical nuclear reactor.
In a light water reactor, you have a lot of solid fuel rods that create chain reactions. And in order to stop the chain reaction, you have to insert what is called control rods that make the chain reaction stop. In a molten salt reactor, it's completely different. If it creates more chain reaction, then the temperature of the salt increases.
Just like any other liquid, when it heats up, it expands, and that leaves a greater distance between the fissile materials. That also means that the chance of a fission reaction will be lower. The chain reaction will slow down a little bit, and the temperature will drop again. So in that way, it sort of revolves around this temperature equilibrium.
The fuel and the heavy water is pumped around all the time through the core. And if we stop the pumps, that means if you press the stop button and you stop sending electricity to the pumps, then the pumps stop spinning and all the liquids in these different circuits will drain out of the core into a dump tank. The whole chain reaction stops. We cannot have the same meltdown event that you can have in traditional light water reactors because these operate in a completely different way.
The overall mission, of course, is to get to a place where we have huge gigafactories around the world, where we can produce one reactor every day per assembly line. Sort of like building cars, where we have huge factories that build a lot of cars and then they distribute it to where it's needed. The price of one reactor would be 50 million US dollars, and that would include the container and then also the fuel and heavy water. And then there is 2 million a year for sort of maintenance. If you divide that by the energy, assuming 90% capacity factor, then that would be $9 per megawatt hour. that is insanely cheap.
For comparison, the cheapest energy source we have today is solar, at about 4.5 cents per kilowatt hour. That would put Copenhagen Atomics right here.
With that amount of abundant and very affordable energy, then a lot of things becomes possible. I mean, we can make clean ammonia, which right now is super expensive, and that can both be used as fuel for shipping and of course fertilizers is being used right now. Data centers, desalination. I think it's so difficult to say what we can achieve if we get so much energy, because it's so hard to imagine what we can do with the future, right? It's imagine the new technologies, the possibilities that we might have in this world. It's probably something we haven't even thought of yet.